We are recording again. I will share the screen, and this session will be an intro to the SciNoj toolkit. I think you see my screen now, and I hope you hear me well. I hope in this session that everybody will just use the voice, to say anything, to ask anything, to comment, and just mute yourself while you're not uh, uh, needing the mic. And yeah, so here we are. This will be the first session of the day, an introduction to the SciNoj toolkit. And maybe somebody can use the voice so I know you can hear me well.
Yeah,
Hello?
I
Yeah.
can hear you. Yeah.
Yeah,
Yeah.
loud and clear.
Yeah. Yeah, great. Thanks. Yeah, and I'll just move a few things around. And yeah, and I think my screen is still visible. And yeah, let us begin. And right, so just to practice the thing that we'll be doing a lot today, here is the Zulip chat, and I'll go to show all topics under the relevant channel, and I'll search for the intro to the SciNoj toolkit. And here we have the topic thread for this discussion where you can comment and write questions and answers and so on. And on the right, I think you see my editor where we will be practicing a little bit of SciNoj. SciNoj is a data science toolkit enclosure. It is something that has been growing in the last couple of years, and it is collecting a few of the relevant closure libraries and tools and so on. Yeah, and thank you, Adham, for commenting on that, right? So let's open the SciNoj website. And right, so why is SciNoj created this way? Yeah, it is a play of words of the word SciNoj, which is like the North Star or something that is used to guide us and find a path, find a clear path. And so SciNoj is the long name for the SciNoj toolkit, where we find a common path for us to practice data analysis in Clojure. It is collecting a few libraries together in a way which is tested together and documented together, so we can make sure that things are compatible. And we already consider it stable in beta stage, and it will keep growing this way. And what I'm doing now is mostly repeating the workshop we had a little less than a week ago, intentionally repeating so people who miss this talk will not miss so much, and we just get to see a little bit of a few of the underlying libraries of the SciNoj toolkit. Later today, much later today, there will be a SciNoj deep dive with Harold, who is one of the people involved in a few of the high performance libraries behind it, and in being very helpful behind the scenes in the chat and so on. So later on, we'll have a session with Harold and myself about more detailed, low-level details of SciNoj. For now, let us just practice a little bit. And does anybody wish to ask anything or comment about anything before we begin?
Yeah, very quick question. What sort of libraries was I'm reading for example like Plotly, TCC, are these inspired from the actual Plotly and the other libraries from other ecosystems? Is there an inspiration, a sort of theme coming from other tools in the data analysis ecosystem?
Oh, thank you. That's a great thought. Yeah, great to mention that. Yeah, so for example, right, tablecloth is inspired by dplyr, which is an R package for table processing, table programming, and a few others. And it is a functional closure way to do similar things that we can see in the R ecosystem. And table plot is inspired by ggplot. But also has Plotly.js target, like ggplot does. No worries if these names are unfamiliar to some people, but maybe for some people it makes sense that ggplot, the layered grammar of graphics, is a certain way of visualizing things that is that some people really love. And Plotly is a JavaScript library for plotting that also has a few wrappers in different languages like R and Python and so on. And both have been combined in the R ecosystem, and here we combine them in a closure-y way, in a functional way. Yeah, thanks. Yeah, and so yeah, maybe let us begin. And what I'll follow is very similar to the workshop we had last Saturday. And so you see, we will be using a certain data set that is actually quite nice for this kind of session because it has very diverse types of data inside, and is also very interesting in terms of the phenomena it discusses. That's a data set of Kickstarter projects, where people are looking to get a project funded. And you may ask, will their project be funded if they propose something? So I'll just, maybe this is the Kaggle website where you can see this data set published, and we can, see the Kaggle way of viewing data that allows us a little peek inside. And you see each row of the data set is a project where somebody proposed something to be funded, like a collection of songs, for example, which is in the category of poetry. And this project did have a certain goal budget, and eventually it failed to reach the goal budget. And in a moment, we'll dive more into these details. And, that's kind of a prediction problem. We may ask, will a certain project fail or succeed in reaching the goal budget they asked for at the Kickstarter platform? Right, so I downloaded this data set and we can read it now, and we are reading it using tablecloth. And you see one way to visualize it is by printing the table in Emacs. It can look like that, and we'll not talk so much about tooling now. We've had longer sessions on that, but you see, it is a table data structure, and it has only 100 rows because we only read 100 rows, right? And any comments, any questions on that? On reading a data set, it is a CSV file which is compressed, and the tablecloth library can just read that. And it is an efficient column-wise data structure that is storing these. One thing you see is that, if we look into this data structure, it turns out it is actually a closure map, a special closure map. So if you ask, is it a map? It will say yes, right? And yeah, maybe let's keep it this way. And so if you ask for the keys of the map, then the keys of the map are the column names, which is kind of convenient. It allows us to explore this data in a closure-y way for those who like closure maps and their keys, right? But probably many Clojure people know that we prefer keywords as keys in Clojure. So let us process these and change them to be keywords. And also there is a little space in one of these, and sometimes it is nicer to not have space in keywords. So when you reading a file and creating a data set, you can process the keys. And
Daniel, just a quick interruption. I think one of your pane panels is obscuring the text editor. One of the panels. Can't see. You see the listing of ID, name, category in the REPL?
Yeah.
I think something is obscuring it for me. Is that happening for other people also?
Yes, that's also happening for me. I believe there is a window that's not being shared.
Seems to
That's
be a window that's
on top of the Emacs window.
Yeah.
Oh, thank you so much. Yeah, I had no idea. Oh, I see now. Right. Yeah. So yeah, that's the Zoom uh, problem. I'll just trying to lay things out in a slightly different way. Many thanks for noting that. And I think it is better now.
Yep. But yeah, better now.
Yeah, thank you so much. Yes.
Except now the Kickstarter project window has become very big.
That's okay. Yeah.
Okay.
I should watch for that. Yeah, thank you. I see now. That's very helpful. Right. So you see, the column names are strings and some of them have spaces. So, you know, in tablecloth, when you're processing a data set and creating this data set data structure, you can process the keys, and this way we'll get a slightly nicer data set where the keys, which are the column names, are keywords, right? And maybe let us define this and give it a name. Let us call this raw projects, right? That will be our data set. And now I'm no longer reading only 100 rows. I did read everything, right? So now, can we print that? Yes, right? So now we have so many rows at this data set. Any comments, any questions on that before we continue? Huh? Yeah. And this data set structure, which is an efficient column-wise store of our column data, is offering some of the usual ergonomics that you may know from data frame libraries in other languages, but also it is very friendly to the closure way of working with functions and vectors and maps and all the usual closure ways. And we will see a little bit of that during this session. One thing we can do with tablecloth is to ask for a summary on this data structure. And you see now we get another kind of table where the rows of this table are the columns of the previous one. And for each of them, we have some summary. So for example, we see that the deadline column of our data set has a date data type, which makes sense, right? The deadline is a date. And you see here are the minimum and value, which is the earliest date we have in this data set. Probably makes sense given that that it is a data set of Kickstarter projects. And you see more information. Maybe another thing you can see is the USD goal reel, which is conversion of the goal funding of projects to the US dollar currency. Here you can see some statistic, like for example, the standard deviation and maximum and mean value and so on. Yeah, and maybe later we'll dive more into that. And one detail here that is a little bit concerning is that we have another date-like column, and that is the launched date, right? When a project was launched. And actually, it is a date-time column. It has values like that. Now, looking at that, we may be a bit concerned, right? One thing is that this value seems very strange, right? For a Kickstarter project, that's, so many years ago. And another thing is that it has a string type. So it means that tablecloth could not successfully pass the value of this column to date time objects, but they remained in string type. So we could take care of that. And I'm glad we're spending time with it, because that's a major part of data processing, just realizing what might be a little wrong and what should be fixed. One way to take care of column parsing is in the main dataset API. The way you create the dataset, you can also provide parser function and take care of that. I will not do it now because I wish to demonstrate another way, and that is actually processing the columns of the dataset. And here you see we define a new dataset where we apply a few operations to our dataset. Maybe let us first print the previous one. That's the raw projects dataset. And here we can, for example, map certain columns. So we can map the USD dollar column with the log transformation and receive a new column that we can call log of the goal, and so on. And so this map columns is a convenient function, and we'll not spend so much time with that. But you see, the point is that you can take a few existing columns and create a new column from them by a function that is applied to their values. And here, the function we apply is some local date time parsing of the Java time library. And this way, when we generate that, we can get the new data set of the processed project. And here, if we ask for the info of that, then what we see is that the launched project is now a local date time type. Local means that it doesn't have time zone information, so it is considered as something just local, right? And so that was a little demonstration of initial data processing. We'll continue a little bit with that. So another thing you can do with tablecloth is the usual group by and aggregate operation, which are familiar from data frame libraries and also from relational databases. So here, for example, we group by the launch year, when the project was launched, and the state of the project that could be successful or failed or so on. Yeah, it would be good, maybe just a reminder, it would be good to use the Zulip chat for questions and answers for this session. And yeah, and one thing we can see is that when we group by and aggregate and count the number of rows in these groups of launch year and state, we can see a few things. Maybe one thing strange that you notice is a few projects that were launched at 1970. This is probably a mistake, right? Another thing you may notice is that some projects are still live, right? Some projects are still live, and that is because it is a live data set that has been, a snapshot of a live data set. And if we are thinking about predicting whether projects succeed or fail, then we need to filter out the live projects, right? So for a prediction problem, we don't want these rows. So, you can do a little bit of data cleaning and take our data set of projects and define the clean projects to be the ones where the year is in the range of years we care about and the state is not live. And what we're seeing now is that this data set we have, which is a column-wise data set, right? Internally, it is represented as a collection of columns. We can process it and consider the rows as maps. So we get the usual joy of closure where we can work with sequences of maps that some of us really like. And the amazing detail here is that the internal representation is such that you can view the column-wise data structure as a sequence of maps without changing the memory representation, without copying anything. It is efficient. And on the deep dive later today, we might talk more about it. But I think for people who like to process sequences of maps, this is kind of familiar and looks convenient. So we have defined our clean projects now. And if we print this data set, we see it is slightly smaller in terms of the number of rows. I see a question now. Yeah. Yes, exactly. Thanks so much, Alex. Thanks for that. Yeah, so that's a good point, right? You have two different ways to add columns, at least two different ways. Let us write a small example. Maybe I'll narrow the code to that. Right. So let us assume we have a little data set where we have x as maybe a range of number, and y as maybe right? Let's create this data set. So now here is one way we can add a column. We can do map columns. And what map columns expect is the name of the new column. The columns it will be computed from, which are x and y, say, and the function that will act on the elements, the values inside the columns. So here, for example, maybe the function will create some strange string, something like that. And when we do that, we get the new z column as mapping this function over the x and y's columns. The other way is add columns, or add column or add columns. So here, what we use is a completely different thing. Here, what we use is a function over a whole data set. So the whole data set will be fed to this function and return a new column. So here, for example, maybe just for another example, we could take the x column and map a function over the x column of the whole data set. So that's a slightly different way of representation. You see here, it is a function that receives a data set and returns a column. A slightly different way to represent that is using the tablecloth column API that allows us to apply functions that already act on whole columns. So we can do something like that. All right, so this is just as the above, using this TCC namespace that has column-friendly functions. Right? So add column receives a function from a data set to a column, and map columns receive a function that acts on elements inside certain columns. Is it okay? Oh, yeah, if there isn't any more, then please ask. Really, thank you for this comment, Alex. And thanks, Adi, for helping. Yeah, right. So, right, returning to that, we see that after we clean the project, we have a reasonable range of years, and we don't have the live projects anymore, which is what we wanted for this session. Oh, Noah, thank you. Yeah, when cleaning data, do you make a copy of the clean version or always derive it from the original source? And does this change if the data updates live? Great. So usually the way we use tablecloth is with immutable data. So usually we will not try to mutate the columns, but we might do that. And most functions of tablecloth are wrapping functions of XML dataset. If we go into the list of underlying libraries of Node, then you will see the famous XML dataset library, which is this high-performance table processing library that lies behind tablecloth. And XML dataset, and then also tablecloth, has this approach that tries to work with references. So, for example, when we filter out certain rows, we will typically not create a new copy of the columns, but create a view over these columns. And there are ways to actually override that, and it depends. There are different functions, but for the most part, what we tend to do in tablecloth is not make a copy, which is quite important for performance. And yeah, what it means is that if we have mutable structures for the columns, then changing them will change the derived data sets unless we make sure to make a copy. Maybe on the deep dive later today, Noah, you could bring that again, and it will be great to show a few examples. For now, it will take us a bit away from the basic intro, but that's a great comment. Yeah. Yeah. So, yeah, thanks. Yeah, that was very helpful. Right. Right, now we will explore the data set a little bit after we've cleaned it. Yeah, we have like 25 more minutes to this session, so we can do a little bit of exploration, and then hopefully have a little bit of the prediction problem we were caring about. Right, so one thing we can do is group by the main category that we have. You see, we have this main category column. We can group by main category and count and order by the count in a descending way. And then you see we have these counts of different categories of projects along the years. Now, can we ask how often are these projects successful? So maybe we shouldn't spend time with all the code, even though we could, right? And we can just compute the success rate. Right, so here you see when we aggregate, we not only count, but do just a little more to, check how often the projects are successful in each main category. So we see the dance category is not so big relatively to others and has great success rate compared to fashion, for example, right? Does it make sense? Any thoughts about this? I think maybe it is a bit unsurprising for people who are used to, relational databases and data frame libraries. I think the main point is that it is all functional and actually quite efficient. Now, let us just make a little plot of that. We'll not talk so much about plotting now, but the point is that we have this table plot library for, layered grammar of graphics, as they call it, as we mentioned in the beginning. And so you see, we can make a bar chart for these success rates of the different main categories and so on. Maybe we'll do a little more of plotting later if we have time. Adham says, can we group by custom means other than the column names? Like, can I segment by value? Can we group by, oh yeah. So I don't remember. And one way to check is go to the amazing tablecloth documentation, which is actually something I'm glad we're sharing. So the tablecloth docs are quite detailed and quite fun to read, I believe. And one thing we can search for is for group by. And it is very common that tablecloth functions allow you more than one way to do something. They have a few different flavors of what they offer. And we see that group by receives a grouping selector. And can the grouping selector only select columns or also be a function? I think it will only select columns as far as I remember. Oh, you can group by a result of grouping function. Yes, you're right, Adham. Yeah, thank you. Yeah, Adham, by the way, is a tablecloth expert as far as I know and has been training people to use tablecloth. So thanks for mentioning that we can, group not only by a column, but by values computed from existing columns. Is that what you meant, Adham?
Yes, and I had a use case for this a while back in something called RFM analysis, where we had like the frequencies of visits, and we wanted to group those into high visits, low visits, and mid visits. So the function was running a cond, and basically the function needs to return a name for the group. So I was checking, hey, is the number of visits like above 20? That gets high. Is it less than 20 but greater than 1? That gets 2. If it's equal to 1, then it gets low.
Oh.
Yeah, so it can be useful for like group by. Once you get into using a function, it can be a very useful tool for segmenting your data.
Oh, I see now what you mean by segmenting. Yeah, yeah, thanks for this comment. That's great. Yeah, great. So what we'll do now is a little bit of data modeling. You know, our hope is to have a certain way to predict whether a project will be successful, whether they reach the budget goal in Kickstarter, right? That's what our dataset is about. And so we'll practice just a little bit of the machine learning mindset, where we take our data and split the data into a training part and a test part, which is, of course, an oversimplified way, an oversimplified mode of more sophisticated things that people do in machine learning. In the SciNoj toolkit, one of the underlying libraries is MetamorphML, which is a machine learning platform that allows you to do much more than whatever we'll demonstrate now. And in the SciNoj documentation, you will find a few tutorials on that. What we'll do now is just a tiny little taste of that, and is not as sophisticated as what Metamorph can do. And yeah, so first, let us say that we wish to predict whether a project will be successful or not using two columns. One column, which we don't have yet, but we'll define in a moment, will say whether it is a theater project. Why am I choosing theater? Because we see that there are many projects of theater main category, and that they have good success rate, right? So I'm already doing something which is a little bit of a mispractice. You know, usually when we conduct machine learning experiments, we carefully split our data into training and testing parts, and whatever we do not use the test set for that, because this way we might actually learn the randomness of the data. And so by looking into this number, which has been computed over the whole data set, I'm cheating a little bit and learning something that is already known about our test data. So you see how easily it happened just because I started analyzing before splitting. And yeah, so I apologize for that. And I'm glad we're seeing that it happens so easily that people can cheat themselves. In this case, it is not so serious because we only learn one number. And in any case, at least we'll technically demonstrate the workflow, right? So we define this vector of two features. One will say whether it is a theater project, and the other will be the log of the goal budget, right? And so here you see first we compute our target column. That is the thing we wish to predict. It will just say whether a project is successful or not. And you know, it just looks into the state and checks whether the project is successful or not. That's the thing we want to predict. Another thing is the theater column that just checks whether the main category is theater. And then we just, you know, focus our data set to only have the columns we care about, which are our two features, our two predictory variables, right? And the target, which is successful, right? And then we split the data set, and this tablecloth split function is part of a whole machinery of many variations, many different practices of splitting data, k-fold and bootstrap and leave one out, maybe are familiar to you. We are using just the simplest way, which is called holdout, which means basically, by default, just split the data into two parts. And let us maybe not think so much about it at this session, which is not, a machine learning session, but just mostly hoping to show that these things are there and we can learn them further if we wish to. Right, so we're splitting the data, and then we are grouping by the splits, and then we're cleaning up a bit. Never mind about this detail. Maybe let us just see the structure we've created. A little detail here is that when we group by, we ask the result type to be a map. So if you remember maybe earlier when we did group by, this just created another data set, which was a special data set called a group data set, right? When we do something like that, it returns a data set of groups, right? And that can then later be aggregated to a summary, right? But now when we group by, we do it slightly differently. Oh, where is our split? Yeah. So now we ask to return a map. So if we look into this split projects data structure, it is actually a map where one key is train, and after this key we have a train data set, and the other key is test, and then we have a test data set, right? So if we ask about the keys of a split of this map called split project, it is just the usual closure map, and the values are two data sets, right? So this is one way to split things conveniently, and then we can just take these two parts and work with them, right? And now here is one way we can do statistical modeling, and in the next hour we'll talk more about statistical modeling. That's just a little taste of that. So what we have here is part of the FastMath library, which is a huge collection of math and statistics library, and is part of SciNoj. You can see it here mentioned, right? FastMath is in version 3 now, which is already stable, but a bit under-documented depending on what part you need. It is in transition, and we'll talk more about that later. And so we're using something called general linear model. Basically, what we're doing is trying to predict our probability of success as a function of a linear combination of the predictor columns. What we mean by linear combination is just adding them and multiplying by numbers. So it will be something like a constant number plus another number times the theater column plus another number times the log column, because these are our two predictor columns. So we are searching for parameters A, B, and C, where this combination called the linear combination of these columns, well, this combination will be a good indicator of the probability of success. Now, of course, this combination might not be a number between 0 and 1, which is what we need for probability, and that is why we need to apply another function here. And the function we will apply is the sigmoid function, which is maybe quite famous and well known to you. And so specifically, we use logistic regression with the sigmoid function. And yeah, we will not dive so much into these details now. We can talk more about them later on other sessions. But the point is that we have a certain formula for the probability of success. And this formula has unknown parameters that we need to figure out. And the statistical algorithm will find those numbers A, B, and C that will be optimal for our data in a certain sense. Optimal for giving decent probabilities to predict success. So that is what we'll do in a moment. I apologize for the noise. There is a big car outside making lots of noise. It will move in a moment. Right? So maybe before I continue, maybe there is a comment or question on that. So the GLM function is very flexible and has many options, and you can see that in the very detailed doc string it has. What we need to predict probabilities is the binomial family, which means estimating probabilities, and this value is for numerical tolerance. We'll not go into that, but essentially these are numerical algorithms. They can run into certain cases where they might not converge, and we need certain parameters to make sure that they will be convenient, and that's a good practice in this case. And you see the data we're passing to the GLM function are the targets to be predicted, and the features, which are theta and log goal, in a form of rows. What is that? This is just the rows represented as vectors. Right? Again, a view over the column-wise dataset, but which is viewed as rows. Right? So that's the way we feed data into the GLM model, and we should have many more sessions on that. This is just a little taste of that. And you see, it may take a moment to train the model. So now I'm evaluating this, and then it is ready. And then the model acts as a function. So we can ask the model, given that theta is 0 and that the log goal is 4, what is the probability of success? Then it will say, oh, 30% success. Right? Given that theta is 1, which means it is a theta project, and the log goal is 4, what is the probability of success? Much higher, right? So we see that whether a project is a theta project or not does matter for prediction here, right? And we can also look inside the model. You see, it is a very detailed data structure. One thing we have inside is the coefficients. And oh, sorry, it's still printing. I'll stop the printing for a moment. I was trying to print that huge structure, right? These are the coefficients. So you see, we have these 3 estimates, which are the estimates for the numbers A, B, and C we mentioned above, right? And you see we have more statistical information about, in a way, about the reliability of these estimates. And we'll talk more about confidence intervals later. And so the model found these optimal values, optimal in a certain sense of likelihood optimization for those who care about it, and don't worry if you don't care about it. right? So it did find those optimal values that will give decent probabilities to work with, right? And now we can return to our data set of test projects and add a probability column computed using the model, right? So, we can add the probability column, and you see these probabilities predicted by the model, they vary. And now we can also even, try to predict and give a sharp threshold and maybe say, if the probability is more than 50%, then let us predict that the project is going to succeed, right? So that is what our prediction does, just compares to a threshold, right? If you like. And of course, this threshold is something you wish to optimize more on, and you can think of the threshold as a parameter to be optimized. But for now, for this session, we'll just pick this 50% threshold, and you see our model predicts that some models will probably fail, and some projects, will probably succeed. And now, of course, we can ask, is this model actually informative with the test set, right? So we can group by the prediction and again check for the rate of success given the two possible predictions of true or false, right? And that's the summary of this session, that this simple model we've created is mostly predicting false, mostly it is predicting failure. And when it predicts failure, the actual rate of success is indeed not so high. So it captures these cases of failure very well. And sometimes it predicts success. And when it predicts success, the rate of success is indeed higher, slightly higher than 50%. So that was a tiny workflow of this practice of statistical learning with a logistic regression model. Logistic regression, which is something that will be mentioned sometimes today and tomorrow in Svetomir's talk, is this idea of taking this linear combination of columns and applying the sigmoid function. In a way, you could also think about it as a neural network, as a very shallow neural network of only one layer. And that's another perspective we see in other talks that will talk about deep neural networks, of course. This session is ending in a moment, and we have short time for a couple of comments, and then we'll take a break before the other session. And bye. Thank you so much, Adi, for this comment, which is very helpful. And yeah, by the way, these are collections of videos and reading materials of different topics that have been collected throughout the years. And if anybody wishes to contribute to that, it would be, of course, great, and let us chat about it. And coming back to the schedule, here we are in UTC time zone. We are just around 9:20 in a moment, and then we'll take a 10-minute break and have the session about probability and statistics. And does anybody wish to say anything or ask anything before we go for the break? We'll have more time to discuss SciNoj in other sessions, and we'll have the deep dive later today for those who can stay for those later hours. And if there isn't any comment or question, then I will just stop recording for a few moments and we'll take a break.
Daniel,
yeah.
do we have like a couple of minutes to show the Noj in a jar, like quick setup, like setup